In programming languages, the associativity of an operator is a property that determines how operators of the same precedence are grouped in the absence of parentheses. If an operand is both preceded and followed by operators, and those operators have equal precedence, then the operand may be used as input to two different operations. The choice of which operations to apply the operand to is determined by the associativity of the operators. Operators may be associative, left associative, right associative, or non-associative. The associativity and precedence of an operator is a part of the definition of the programming language. Different programming languages may have different associativity and precedence for the same type of operator. Consider the expression A tilde B tilde C. If the operator tilde has left associativity, this expression would be interpreted as tilde C. If the operator has right associativity, the expression would be interpreted as a tilde. If the operator is non-associative, the expression might be a syntax error, or it might have some special meaning. Some mathematical operators have inherent associativity. For example, subtraction and division, as used in conventional math notation, are inherently left associative. Addition and multiplication, by contrast, have no inherent associativity, though most programming languages define an associativity for these operations as well. Many programming language manuals provide a table of operator precedence and associativity. See, for example, the table for C and C++. The concept of notational associativity described here is related to, but different from, the mathematical associativity. An operation that is mathematically associative, by definition, requires no notational associativity. An operation that is not mathematically associative, however, must be notationally left, right, or non-associative. Examples. Associativity is only needed when the operators in an expression have the same precedence, usually plus and have the same precedence. Consider the expression 7 minus 4 plus 2. The result could be either plus 2 equals 5 or 7 minus equals 1. The former result corresponds to the case when plus and minus are left associative, the latter to when plus and are right associative. In order to reflect normal usage, addition, subtraction, multiplication, and division operators are usually left associative, while an exponentiation operator is right associative. This applies to the up arrow operator as well. Any assignment operators are also typically right associative. To prevent cases where operands would be associated with two operators, or no operator at all, operators with the same precedence must have the same associativity. A detailed example: consider the expression 5 4 cubed squared, in which caret represents exponentiation. A parser reading the tokens from left to right would apply the associativity rule to a branch, because of the right associativity of caret, in the following way. Term 5 is read. Non-terminal caret is read. Node 5 caret. Term 4 is read. Node 5 4. Non-terminal caret is read, triggering the right associativity rule. Associativity decides node 5 caret. This can then be evaluated depth first, starting at the top node. The evaluator walks down the tree, from the first, over the second, to the third caret expression. It evaluates as 32 equals 9. The result replaces the expression branch as the second operand of the second caret. Evaluation continues one level up the parse tree as 49 equals 262,144. Again, the result replaces the expression branch as the second operand of the first caret. Again, the evaluator steps up the tree to the root expression and evaluates as 5,262,144. 6.206069 times 10,183,230. The last remaining branch collapses and the result becomes the overall result, therefore completing overall evaluation. A left associative evaluation would have resulted in the parse tree cubed, squared and the completely different results 625, 244,140,625 and finally tilde 5.9604645 times 1016. Right associativity of assignment operators. In many imperative programming languages, the assignment operator is defined to be right associative, and assignment is defined to be an expression, not just a statement. This allows change assignment by using the value of one assignment expression as the input of the next. For example, in C, the assignment A equals B is an expression that returns a value with the side effect of setting A to this value. An assignment can be performed in the middle of an expression. The right associativity of the equals operator allows expressions such as A equals B equals C to be interpreted as A equals, thereby setting both A and B to the value of C. In C, the alternative equals C does not make sense because A equals B is not an L value, just an R value. However, in C++, an assignment A equals B returns a value referring to the left term in the assignment. Therefore equals C can be interpreted as A equals B, A equals C. Non-associative operators. Non-associative operators are operators that have no defined behavior when used in sequence in an expression. In Prolog, the infix operator is non-associative because constructs such as A, B, C constitute syntax errors. Another possibility is that sequences of certain operators are interpreted in some other way, which cannot be expressed as associativity. This generally means that syntactically, there is a special rule for sequences of these operations, and semantically the behavior is different. A good example is in Python, which has several such constructs. Since assignments are statements, not operations, the assignment operator does not have a value and is not associative. Chained assignment is instead implemented by having a grammar rule for sequences of assignments A equals B equals C, which are then assigned left to right. Further, combinations of assignment and augmented assignment, like A equals B plus equals C, are not legal in Python, though they are legal C. Another example are comparison operators, such as greater than, equals, and less than equals. A chained comparison like A less than B less than C is interpreted as A not equivalent to either less than C or A less than.